Hello, Diptanu. Hello. Hello, Diptanu.
Rajesh, can you hear me? Hello.
Yes, sir, your voice is clear.
Okay. Thank you.
यस सर, यस सर।
इकोइंग हो रहा है राजेश आपके उसमें।
सर अभी नहीं होगा ना।
हाँ, 2 डिवाइस मत खोल के रखना, एनीवन।
ओके सर, ओके सर।
Good evening, Sharma ji.
Good evening.
Good evening. How are you?
Yes, भैया.
बढ़िया. Okay, just so can we start? 32 are there, 30 plus.
Hey, you can wait for 3-4 minutes. Others
Acha,
can
okay, 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 okay. Dr. Ankush, can I start now?
Yes, please go ahead.
Okay. So, good evening, one and all. At the onset, I welcome you all in the first session of the first day of ATAL FDP on power quality disturbances in smart distribution grid, theories, concepts, and solutions. We have with us Dr. Ankush Sharma. Dr. Sharma is currently working as Associate Professor in the Department of Electrical Engineering at IIT Kanpur. Prior to joining the IIT Kanpur, he was working as Assistant Professor in the School of Electrical Sciences. In addition to academic experience of around 6 years, he has close to 16 years of industry experience, primarily in the power system and the smart grid domain. Dr. Sharma obtained his BTech in Electrical Engineering from Harvard Butler Technological Institute, Kanpur, MTech and Ph.D. from Indian Institute of Technology, Kanpur. He obtained various awards in academic and professional career, including Fosuco Power System Award for Best PhD Thesis Work. He also received various appreciation and accolades during his professional and academic tenure. He is a senior member of IEEE. His research interests are power system state estimation, wide area monitoring system, IT application into power system, smart grid and smart city technological development, real-time simulation, energy management system, distribution management system. So with this brief intro, I would like to request Dr. Ankush Sharma to start the first session of the first day. Dr. Sharma, please.
Thank you, Dr. Jain. Let me share my screen. Yes. I hope you can see my screen, right?
Right now it is not appearing.
Maybe some slight delay, I think.
Okay, maybe.
Did you see my screen now? No.
No, not yet.
Okay, just a minute. Let me try once again. You can see now?
Now it's okay.
Okay. So, good evening to all of you. So, in today's session, we will discuss about basics about the smart grid technology and how we will use that technology for smart distribution grid. Then also we will discuss about the renewable integration, its challenges, and in the last I'll give you an overview about one case study. In fact, this is our Indo-US project where we are deploying the smart distribution system with renewables and storage. So I'll tell you a brief about that particular pilot project also. So let's first start the discussion related to power system automation, because power system automation is the most important component in the smart grid technology, because everything we are now planning to automate. So we want some minimum human intervention in operation of the power system. The reason is that the response of the human being is slow when you compare with the machines. So that's why we want to make more automated operations than the manual operation. Now, if you go back to the history of automation, you will see that we started automation in early 1900s year, and in fact by 1920 we were in a position to develop the relay logic, because in late 1880s and 90s we saw a big debate on DC versus AC, and eventually AC won because of the long distance power sending. Because of that, lot of AC distribution systems started coming up. The major challenge with the distribution systems was that though those were very small, but protection was the major challenge. So that's why we saw the evolution of relay logics in around 1900 to 1920. In fact, we talk about supervisory control and data acquisition system, but you will be surprised to know that we started working on SCADA concept in 1920 only, although the actual word, which is SCADA, supervisory control and data acquisition system, emerged in 1960s, but some analog controls and the algorithms based on analog computers was developed during that time. Why it was required? Because some of the distribution systems were started interconnecting with each other for power transfer. So because of the interconnection, lot of issues started happening, and we wanted to address those challenges, and that's why the power system automation was required. We were not having any digital computer at that time, so that's why most of the time analog computing machines people used to use. Then in 1950s we saw the development of economic dispatch and automatic generation control, which actually considered as a advent of our energy management system. So you can say that economic dispatch was the first application which was utilized in our power systems. Then if you further go forward, you will see that in 1950s, in fact, if you talk about 1959, we started the use of digital control systems, because at that time the digital computers were started coming up in the market, and we were having now the semiconductor technology available in the market for better computation purpose. So you can say that 60s were the time period where we see the actual evolution of digital control. So we started then digital computing, and then other software applications development during that period. Now the problem again came in different form. What happened that since the computers were new, different vendors used to develop their own operating system, and they were kind of tying up the application software with their own operating system, and this caused the monopoly of the software solutions. What happened because of that? So problem happened because if you want to change the application, you have to completely replace the operating system and the computer, and this was a huge cost involved in replacement, and utilities were struggling because they were kind of not comfortable in replacing the complete system, rather than they wanted some evolution of open standard. So people thought, and then they started coming up with the open standards, which actually started in late 90s. And after that, as you may be knowing, that we started the evolution of SCADA protocols, that is IEC 60870, and different series were there, 101, 104 protocol for series and parallel communication. So for that particular aspect, we saw the evolution of such kind of protocols. In fact, to some extent, Windows also standardized the operating system, and a lot of software application started coming up. From network point of view, if you see that in 1982, we saw the evolution of RS 422 and 485, which was considered as an open network protocol. Now, what used to happen before that? So before that, we generally use telephone wires for the data communication. That's why if you see the name of SCADA protocols, they are called as telecontrol protocol, because at that time when the protocols were developed, most of the utilities were having telephone lines for data communication. That's why those are called as telecontrol protocol. Now, then you see other protocols coming up like DNP3, and we started having the increased data bandwidth, and a lot of data we can transfer from field to the SCADA server. Then if you see the computer network evolution, we see that in 1970, the ARPANET was the first network to implement the protocol suite, which later became TCP/IP. And by 1990, we saw the use of TCP/IP in a big way, and this ARPANET project was decommissioned because this became commercially available. So Ethernet, which is another protocol for data communication, was developed and standardized in 1983. Then we saw the Unix, TCP/IP for Unix in 1989, and then for Windows, IPv6 was developed and proposed in 1998. In fact, first .com registration happened in 1985. World Wide Web was developed in 1991, and then Wi-Fi, which we use more frequently now, was developed in 1999. So that is IEEE 802.11b was the wireless networking, which was introduced in 1999. So you can see that our power system automation was quite ahead of the evolution of information technology, and this actually created problem for power system engineers, because most of the things which we developed were not compatible with the latest IT tool, and this happened because of the late evolution of information technology. Then why we are talking about smart grid? Because a lot of things happened in the past related to the evolution of power system as well as the evolution of information technology. As I discussed, by 1960s we were having quite matured power system network, and we were started using the softwares like SCADA for better monitoring and control of the power system network. And since we reached almost economy of scale, and almost by late 1960, most of the population in developed countries had access of electricity. This, in fact, raised the demand for electricity in different distribution systems. Once you have the sudden jump in the demand, you suffer the power quality and frequent blackouts. So 1970 to 1990 was the period where we saw a lot of blackouts, power cuts, brownouts, and that's why industry demanded higher level of reliability. So this was the initial triggering point, although we were not having sophisticated technology, as I mentioned, that IT was not that mature in 90s, and because of that we were not having much sophisticated tools for better monitoring and control of the power system network. In late 2000, peak load management happened, and because of that, we saw redundancy in the grid increasing, and this resulted in high cost of electricity. And if you remember that California crisis, this happened because of the increased tariff of electricity. So all these cumulative were the precursor to the evolution of smart grid. And then we saw in early 21st century that we got better communication and IT technologies. Sophisticated control systems were developed. In fact, wind power and solar power started coming up in the system and getting integrated in the power system network. And then you saw the grid topology being highly distributed, bidirectional power flow, and then growing concern of the cyber security, because now more and more IT infrastructure we were using in the management of energy grid. Then triggering point happened in the in 2003 when we saw the biggest blackout in US history, and this happened on 15th of August 2003. This gave rise to the triggering of the concept called smart grid. So although we were having a lot of challenges in the past, but 2003 US blackout, which was biggest in the history, gave the momentum to the evolution of smart grid. And in 2007 we saw the act in US, which is called Energy Independence and Security Act 2007, which talks about the smart grid and electric vehicle interoperability. A lot of things this particular act talks about, which became the building block of our smart grid technology. Now let's see the current structure of power system. You know that we have unidirectional power flow, traditionally designed power system with unidirectional power flow, where we have generation, transmission, distribution, and then the power goes to consumer premise through meter, and then the loads get the power. What changes we see in the power sector? The first and major change is the alternate and renewable energy sources being added into the power system network, because we need to address the global warming challenge. And if we are not acting upon, we will see that by 2050 we will see the rise of 1.5 degree in global temperature. So that's why a lot of governments are pushing up the addition of renewable energy sources in the power system network. The development and deployment of new electronic devices we are seeing increasingly being deployed in the power system, because once you have renewable energy sources, you need power electronic devices to convert DC into AC or AC into DC if you want to store, and then a lot of sensors and information and communication technology is being used. Then off-grid and grid-connected microgrids with renewable sources are coming up, which includes storage as well. So a lot of islanded microgrids and grid-connected microgrids are being developed. This helps in making the small section of load self-sufficient, but it poses more challenges, because the moment you have fault in the system, your islanding operation of the microgrid needs to be addressed properly. Then we are also seeing the integration of electric vehicles and the charging infrastructure, IT-enabled services for maintaining the power system security, reliability, resiliency, and which gives rise to better wide area monitoring of the system, ADMS, and other smart grid concepts. Then because of this, you also try to address some other regulatory and market challenges. So these are the key changes we are seeing right now in our power system network. How we monitor the power system right now, so whether it is a transmission or distribution system, the power is being power flow or injection or voltage or any other electrical parameter which we want to monitor is being monitored through SCADA system, that is supervisory control and data acquisition. How it works at the field, you need a device called remote terminal unit. In some location you will also see that PLC is connected. PLC is nothing but programmable logic controller. So what is the role of RTU? So in the field, we have two major sensors, at least for power system network, and these are current transformer and potential transformer. So you take the measurement of voltage and current through potential and current transformer. Then those analog values come to RTU through control wires. Then it gets digitized using analog to digital converter in RTU. Then you do initial filtration of the digital data which you have just now captured. And then you process that digital information by packing into a particular protocol. And then using that protocol, you send data to the remote server. So what we use for communication, the protocol we use for communication is IC 60870-5-104 if you want to go for network communication, or if you still have serial data communication, you will use 101. Now via router, the data reaches to SCADA network. Here the communication medium can be anything. You can use optical fiber, you can use maybe GSM, GPRS or Wi-Fi. So depending upon how and what is the distance of device from control center, you can decide what kind of communication mechanism is required. So once you reach at the control center, you have control center network, which is nothing but a SCADA network. You get the data here, and then you give data to application server, where a lot of applications including SCADA are running for visualization. So this information goes to your HMI station, where you see the single line diagram and then the parameters which you have captured from the field. You may need to store the data for historical purpose, and then if you want to share data to another control center or to the outside world, even using firewall, you can share data to external network. So this is how SCADA system works in the control center. In India, as you know, that we have various power system sub-networks divided in the form of sub-local load dispatch centers, or state load dispatch center, or regional load dispatch center, and then national load dispatch center. So in fact, in India, we have 5 regional load dispatch center: north, south, east, west, and northeast. And then every component of the data is consolidated at national load dispatch center. Every state has state load dispatch center for monitoring of state level data. So once you capture the data from RTU or maybe any other intelligent electronic device, you share data first to sub LDC if your SLDC size is big enough, or you can send data directly to SLDC. Generally, sub LDC is the set of substations where you first consolidate the data, and then consolidated amount goes to SLDC, and then from SLDC to RLDC, and then it reaches to National Load Dispatch Center for complete country view. Now, if you see in each and every data communication, you are adding some delay. At RTU to sub LDC, you may add some 10 seconds of delay, then sub LDC to SLDC, again 10 seconds, then RLDC, and then NLDC. So if you see in complete chain, you kind of delay the measurement reaching to NLDC by say 50 seconds to 1 minute. Now, if you see the operation of the power system will take only 3 to 4 seconds to go from healthy state to collapse state. So you generally have very less time window for taking action. And that's why we are not having much visualization or real-time visualization with the help of SCADA system, because the moment you send data from this to NLDC, you have already changed the state of the power system and you are getting the delayed measurement by around 50 seconds or 1 minute. So the challenges which we right now have in SCADA system is that we have slow data reporting rate, as I mentioned in the last slide. Then if you see that we have centralized architecture, everything from downstream to upstream is being consolidated with the help of centralized architecture. And most of the time we use client-server driven architecture for SCADA visualization. It is incapable to handle the large amount of data because SCADA was developed in late 60s, where the size of data was very small. In fact, telephone lines were sufficient to handle the data. Now we are having more sophisticated technology, especially the information and communication technology. We have more sophisticated electronic devices where we are exchanging the data in large amount. So because of that, the inherent structure of SCADA system is that you cannot handle the large amount of data. Then you see that most of the time you will have SCADA system operator driven, because once you see the data on single line diagram, whenever any event happens, operator has to acknowledge that alarm and take action based on that. So most of the time you will see that operator has to be there 24/7 to address any event which is happening in the power system network. So that is another limitation for SCADA system. Security issues are there because when the SCADA system was developed, there was even no one was aware that there is something called cyber security, because their IT infrastructure was not developed to that level. Now we have seen the SCADA system developed in silos and IT infrastructure developed in another different isolation. We are seeing a lot of challenges in SCADA system because it is now vulnerable to cyber attack. We are still using legacy protocol because that is the only answer we have right now. So that's why we need more sophisticated tools and alternate of the SCADA system, which can enable the real-time monitoring and control of the power system network. Then data interoperability is another issue because SCADA system is designed for a traditional way of data communication. So new devices find problem in getting integrated with the SCADA system. We also have new technology integration issues. So for example, you may be aware that we have phasor measurement units which can scan and measure the data at the rate of 50 frames per second. If you want to integrate PMU with the SCADA system, you face a lot of challenges because the data reporting rate of PMU is very fast when you compare with the legacy RTU system. So that's why we have a lot of limitations in terms of new technology integration. Dynamics, you cannot visualize. As I mentioned, once you get the data at National Load Dispatch Center, it's already 1 minute delayed. So dynamic operation or dynamic visualization of the system is not easy in the SCADA system. Environment is not open because most of the time this SCADA system is supplied by limited vendors. So they try to hold the control of the SCADA system market, and there is very less open source solutions available for SCADA system. They try to monopolize the SCADA solutions in the market. It has limited complexity handling because when you have large data, the SCADA system sometimes hangs and it doesn't have much capability to handle large amount of data, and because of that we cannot build any complex data processing algorithm inside the SCADA system or maybe energy management system which sits on top of the SCADA system, or distribution management system which also sits on the SCADA system. So depending upon what kind of network you have, say if you have the distribution network, on top of SCADA you will install the distribution management system where you have a lot of software applications like a distribution system, state estimation, load shedding, fault correction or isolation and restoration activities, then optimal network reconfiguration, crew management. All those software applications are built as part of distribution management system, but those are having very limited capabilities because you cannot build more complex algorithms in that kind of structure, and we do not have the robustness in the SCADA system because of the inherent legacy which we are carrying along with the SCADA system. Now you might have listened multiple times IT and OT. Let's first try to understand what is IT, what is OT, because this will keep on we will keep on using these terms for other discussions when we will proceed. So basically information technology is nothing but that set of applications which are mainly used for storing the data, processing the data, mainly for business or enterprise environment. Say for example, your billing system, MIS system, or dashboard creation, ERP solution, customer relationship management system, all those applications are business applications which are built as part of our IT infrastructure. So if you see information technology is built as a top-down approach where top management decides that they need some information from the lower functions, and then accordingly the various functions are developed and being used in the system. So you can see that the evolution of IT started in 1970s, late 70s. You see the evolution of local area network. In fact, 1982, 83, you see the evolution of Ethernet, and in fact, World Wide Web started in 1990s, wireless in 2000, and now we are seeing a lot of new technologies like cloud computer, big data, IoT. These all started in just 10 years back. So you can see that the information technology domain is very nascent. It's new when you compare with the operational technology. operational technology, if you see, is the set of applications which are used for field level operations. So, for example, if you are working in a processing plant, you need a lot of sensors to process the product development, or if you are in a chemical plant, you need different sensors to assess the concentration of gas and pressure and so on. So once you hit the ground operation using any technology, those are clubbed as operational technology. Operational technology generally use the sensors and limited amount of data for processing or controlling or operating any device or any visualization. So operational technology and information technology are entirely opposite. Operational technology is bottom-up approach where you acquire data at the bottom and then you visualize at the upper level. While information technology is the business case where someone at the top decides what kind of the data we need to acquire from the different vertical functions which are there in the particular organization. So because of these two different directions, we see a lot of challenges in integration of the information technology and operational technology. We also see that the modern operational technology started its evolution in 1950s, which you can see that around 20-25 years before the actual evolution of information technology. So because of that, it's like a parent-child relationship. OT people doesn't want IT people to come into their domain, and IT people cannot understand what OT people are doing. So both are being developed in silos, and this created a divergence in the IT and OT technologies. What we need to do now, because we have a lot of challenges and we need to address those challenges when we talk about the smart grid technology. As I have mentioned that IT has developed from top-down approach and OT has developed from bottom-up approach. Because of that, we see very limited cross-domain knowledge. As a power system engineer, we know the different operational technologies or applications because we are taught in the course. Like we know what is SCADA, what is state estimation, what is your volt-var control, what is our load shed, how it works, right? How we do the feeder reconfiguration, how we do the loss minimization, all those things we study because those are mostly related to operational technology. But we are not taught the information technology, like how the computer network works, how operating system interact with the data packets, how the different software applications are built, which OSI layer works for what purpose, how your IP version 4, IP version 6 work. All those things are there in IT domain, but we are not taught in our regular course curriculum. So because of that, we have very limited knowledge of information technology, and we are not in a position to add more value in terms of IT into our different OT applications. And the reason is simple, because OT is more proprietary in nature, because OT generally is being taught for power system engineers or electrical engineers or chemical engineers. But information technology has become more generic. Everyone at some point of time reads or tries to understand the information technology. So IT people are not in a position to understand OT because OT is very niche in nature. You cannot teach a computer science engineer about the power system. So what is the answer? Answer is that at least to some extent we have to understand the working of information technology. then only you can cross that barrier, because until unless you understand the information technology, you cannot bridge the gap between OT and IT. Why we need? Because once you deploy the operational technology system, say for example, you have developed the outage management system for distribution network. Now this outage information you want to share with your customers. So definitely you need outage management system data to travel to customer relationship management system, that is CRM. But OMS is OT application, CRM is IT application, and you do not know how to integrate OT data with IT data, and their problem is happening. We are not in a position to share OT data, or in this particular case OMS data, with the CRM data, with the CRM application. So what we do generally, we take the OT data in some intermediate format, say Excel or any other database we port, and then from there CRM application picks the data. So because of this intermediate layer, we have inherent delay, as we saw in case of SCADA. The same will happen with the IT/OT integration. So that's why we need proper integration of both sides of the technologies. Why we are seeing the barrier? Because we have multiple data sources in OT, while in IT we have much structured database and much structured data sources. Tools such as SCADA or distributed control system, they are not ideal for data manipulation. They give data in different format which IT applications cannot understand easily. And in fact, you know, the power system is niche domain. You cannot share the knowledge related to power system with the computer engineer. So there is a huge requirement of integrating IT and OT, and this is possible only if we can understand the information technology. So in distribution system, when you want to make the next generation of smart distribution system, you need to understand the nitty-gritties of IT systems, because all applications are driven by the IT tools, or in fact new devices such as smart meters or phasor measurement units are more considered as an IT devices, because they are more structured when you compare with the legacy RTU and other devices. And in fact, when we talk about more real-time visualization and then evolution of smart grid technology, we need our staffs to be trained for IT and OT both. Then if we can understand IT, then we can use more sophisticated tools like big data, cloud, or IoT for real-time visualization, monitoring, and control of the power system. So the need is that you should capture the best practices of both sides so that you can get the best of both worlds. What benefits you are going to do? Since we are integrating IT and OT, you will have better automation, sensing, and visibility. You can deploy the solution to make the visualization or operation in almost real time. You will have more flexibility because you can use more updated or new technologies in the power system network. Better compliance with regulatory requirement, improved organizational performance because your delay will be avoided, more effective workforce because you need to keep only one type of workforce, whether it is OT system or IT system. Why you will keep different sets of people for OT, different for IT? So you will optimize the workforce. You can have better decision making capability, improve customer satisfaction because, as I gave you the example, when you are using outage management system, you can immediately integrate with the CRM, and CRM tool will send the information in terms of SMS or maybe the network push about the outage information. So informed customer will be more satisfied, and that's why we'll have the better stakeholder satisfaction. What recent changes we are seeing in the distribution sector? We are seeing that there is a large deployment of rooftop solar and ground mounted renewable energy sources. This is causing another kind of challenge, which is in terms of addressing the faults, because the traditional power system has more inertia, and when you have more solar integration in terms of rooftop or maybe large solar farms, your center of inertia reduces, and this impacts the fault addressing capability of the system, because when you have more inertia, small faults can be addressed with the inertia of the system itself, while in case of renewable we will have different kind of challenge with reduced inertia. Advanced metering and ICT infrastructure, because when you have more smart meters deployed in the system, you have more information and communication technology requirement. Then you see a lot of microgrids are also coming. So you see greater integration of renewables and storage at community level or maybe even at distribution system level. Energy storage in the form of grid connected as well as off grid. That means flexible energy storage system, say electric vehicle is also your flexible energy storage system. So those are also getting integrated into the distribution system, which is again impacting the performance of the distribution system, because sudden addition of any electric vehicle into the system for charging will have impact on the performance of the distribution network. Then see different reforms which have been initiated by Government of India, like APDRP, RAPDRP, IPDS schemes, Deen Dayal Upadhyay Gram Jyoti Yojana, Ujjwal Discom Assurance Yojana, Revamped Distribution Sector Scheme. So all these initiatives are coming for the distribution system, which have their own targets. In this revamped distribution sector scheme is the newest one, because with this government is trying to modernize the distribution sector by adding more sophisticated tools in the form of ADMS, Advanced Distribution Management System, Geographical Information System, GIS, better fault addressing mechanism, and so on. So now the distribution networks are transforming themselves into active distribution network with bidirectional power flow. So this bidirectional power flow is very important, because you are now having more distributed energy sources in the distribution system. So at lightly loaded condition, you will see lot of power is pushed back to the distribution system by these renewable energy sources. For that, the distribution system is not designed traditionally. So you need more sophisticated tools and techniques to address those challenges which are coming in the distribution system. Now, if you talk about the definition of a smart grid, so you need to just remember these 4 R's. The system which is resilient, reliable, robust, and reconfigurable, you can consider that power system network as a smart grid. So there are a lot of definitions reported in the literature. So one such definition given by James Momo, which says that a smart grid is an advanced power system network which is having two-way digital as well as electrical power flow, capable of self-healing, adaptive, resilient, and sustainable, with foresight of prediction under different uncertainties. It is equipped for interoperability with present and future standards of components, devices, and systems that are cyber secured against malicious attack. So in this definition, James Momoa has covered all important aspects in the power system network which are required to be built. Then NIST USA, that is National Institute of Standards and Technology, has given the definition which says that a modernized grid that enables bidirectional flow of energy and uses two-way communication and control capabilities that will lead to an array of new functionalities and applications. IEEE definition says that a smart grid is a large system of systems where each functional domain consists of three layers: power and energy layer, communication layer, and IT computer layer. Then layers 2 and 3, that is the communication layer and IT layer, are the enabling infrastructure that makes the existing power and energy infrastructure smarter. Let's see how we can make the power transmission or distribution system smarter. So as I mentioned that in our traditional power system network, we have only unidirectional power flow, that is from generation to transmission using various step up and step down transformers. We reach to the distribution network, and then from distribution network to load ends. So that is the traditional way of the power system architecture. What is changing? The problem is happening because of wide geographical spread of the power system network. We are seeing a lot of different load centers coming up, different conventional and non-conventional energy sources are coming up. So your size of the power system network is increasing. Lot of interconnections are coming up. Rapid growth in demand of electricity is coming because of the heavy dependence on the electricity now. Power system components are now being operated closer to their design limits, and penetration of renewable energy sources and competitive electricity market is forcing us to go for more sophisticated power system network. What transformation is happening? This is our traditional way of power system operation: generation to transmission, transmission to distribution, and then through distribution network we have different kinds of loads, maybe industry, commercial, or residential. What is happening now, because of the integration of different energy sources like rooftop solar, wind farms, microgrids, electric vehicles, or in fact energy storage or large scale renewable penetration, the distribution is now becoming bidirectional. Sometimes it is pushing power back to the distribution network, and from distribution network to back the transmission network. And now this is a challenge because our system is not designed for backward power flow. So we need proper protection, monitoring, and observability mechanism so that we can address these challenges which are happening in the system right now. So particularly the distribution system is more challenging because it is seeing the large change in the distribution system power flows. In fact, during daytime it will be lightly loaded because of the solar penetration. We do not know the real load because most of the load will be compensated by the solar PV system. But suddenly in the evening, after 5:30 or 6 p.m., we see the sudden jump in the demand. And that demand is something which is very difficult to meet in real time because your generation will be ramped down because of the lightly loaded distribution network. It will need some time to ramp up. So real-time balancing of the load and generation is very challenging task in today's power system network. Then what we need to do, we need proper ICT communication backbone where each and every equipment and each and every appliance which is there in the power system network needs to be IT or ICT enabled, where we can remotely communicate with those devices for control or data acquisition. So this is now the requirement in our power system network, where a lot of data we need to capture from end devices. What are the different building blocks we are seeing in the smart distribution system? First is the distribution automation. So we started our journey with distribution automation, where small automation activities like in the form of relay operation, breaker automation, all those things happened. Then later we switched over to substation automation, where we added intelligent electronic devices. We made the substation IC 61850 enabled, where every aspects of the substation operation is automated, and almost in real time the operation can be taken place with the help of substation automation. Then we saw the integration of advanced metering and communication technologies. In fact, in India, we are right now moving towards the 100% smart metering in cities. Slowly, they will penetrate into the rural areas also, because advanced metering infrastructure has its own advantages in the form of better monitoring of the load. In fact, you can remotely disconnect the meter for those cases where you see that the energy theft is happening or the customer is not paying the bill. Then synchrophasor measurements, these started its integration in the transmission system, but they are slowly going into the distribution in the form of microphasor measurement units, and it is enabling the wide area monitoring and control of the power system network. Then you need distributed intelligence, because if you centralize the intelligence, the decision making will be delayed. So you need distributed intelligence. In fact, at each and every device level, you have some intelligence to be built so that the response of the system is quick. And then you go for various software enterprise applications for better monitoring control operations, and then evolution of various IT applications or IT technologies like IoT, data analytics, and cloud computing. What are the differences between conventional grid and a smart grid? So from architecture point of view, if you see, the conventional power system network is hierarchical, while your smart grid is more unbundled and distributed in nature. When you talk about consumer participation, most of the time you will see that in conventional power system, the consumer is not non-participative and very less information is shared with the end consumer. In fact, only once in a month you will get the billing information and your load consumption information. While in the smart grid, we are seeing that with the integration of advanced metering infrastructure, you can even see your load profile in real time. Then generation and storage operations. Most of the time in conventional power system, the generator are in dominance, storage framework is not there. While in smart grid, we need distributed energy resources with plug and play features. So your dominance of the central generator has gone with the advent of smart grid technologies. Power quality. In conventional system, we have poor power quality. Focus is mostly on outage. Well, in the smart grid, we see power quality is the priority. When we talk about new product and services, very limited or poor customer focus is there in the conventional system. In smart grid, we can have better market and services for customer. We can see the the energy meter portability, similar to what we see in case of mobile number portability in near future. Because if you are not happy with one service provider, you can switch over from utility A to utility B. So this is what is already happening in different parts of the world. In India, we are still not in a position to reach to that level, but soon we will see that type of energy service providers coming in the distribution system. Then asset optimization is very poor. We have hardly any data related to the loading of the different devices like transformers in the conventional system, while in smart grid we are seeing more data driven approach. In fact, predictive asset management or reliability centered maintenance will be key in the smart grid. Self-healing is not enabled in conventional power system network, while in smart grid you need self-healing because your system should recover itself from any fault or any abnormal condition without any human intervention. Then cyber attack, you need smart grid to be resilient to cyber attack. So unlike conventional power system network, you need to build cyber security resiliencies applications in the power system network. Disaster management is very slow and reactive, while in smart grid we have more proactive and quick response to the disaster, because when we have informed decision, our response will be faster. We already know that these weather websites show the possible adverse weather condition, maybe cyclone or any other such kind of activity. If we can integrate that with our power system network, we can easily see that what are the equipment which are likely to get impacted. Based on that, you can take decision for quick restoration, which is not happening right now in our existing power system network. Since we do not have data, so we have very less event analysis possibility in the conventional power system network. While in smart grid, we forecast smart analytics with the better load or generation forecasting capabilities. Communications, mostly one-way communication happens in conventional, while in smart grid we are seeing the integrated two-way communication. Predictive algorithms are not there in the conventional power system network, while we need predictive processes and applications in smart grid, because we need to predict well in advance before we see any possible collapse of the power system network, which is not there right now, and we need such kind of solutions to be built so that we can avoid any possible blackouts or brownouts in the system. Limited intelligence we see in the conventional system, while in smart grid we will have more sophisticated intelligence, and we have the capability to process the critical information in real time. Poor efficiency is there in conventional, while efficiency will be focused in smart grid. So these are the typical parameters through which you can judge about the readiness of our power system network towards smart grid. Now, what are the different domains we have in smart grid? So traditional domains are there, like generation, transmission, and distribution, but some other new domains are coming up in the smart grid definition. One is better customer participation, operations, energy market, and service providers. So if you see this figure, you will come to know that lot of communication is happening between different domains, while actual power transmission is happening between these four domains only, right? So that's why we see that in future, when we switch over to completely smart distribution or transmission system, we will see the value of bits more than the value of electron. So in a smart grid, we can say that the bits are or bytes are more valuable than the electrons. Customer domains, if you see that contains different kind of customer segments, commercial, industrial, and home. In these three domains, you will see a lot of automated devices because you need more data communication and information sharing. So through different gateways like home gateway, building gateway, or industrial gateway, you will share this information with various entities like service provider, operations, distribution, and energy markets. In market domain, your more focus would be to get information from different domains almost in real time, because you need to take decision that when and what amount of energy you want to trade in the market. Service provider, this is the domain which is slightly new in the smart grid, because once you have more penetration of different information and communication technologies and more devices, IoT devices in the system, or the more integration of renewable energy sources, you need different kind of service providers. Out of these, retailer and aggregator is more common. Retailer means the company which is taking care of your energy bills requirement or any meter related activities or related to any power distribution issues. So retailer you can change, like mobile number portability, you can change your retailer company. Aggregator means that entity which is in a position, which is having a capability to aggregate the different renewable energy sources and trade on behalf of you in the market. So 5 kilowatt renewable which you have on rooftop may not have that visibility in energy market, but if 100 such customers, this aggregator aggregates 500 kilowatt, he can trade in the market. So aggregator will aggregate the solar generation which is distributed, and it will trade or negotiate with the distribution company for any possible economic benefit. Other than that, you will have a lot of other service providers like your technical services provider for solar, for energy storage, for your home appliances which are now being IoT enabled, or home controller. So a lot of such kind of service providers will come up in the domain. Then operations means your real-time operation, maybe it is network operation or the maintenance or supply chain or any such kind of operation which is required for the effective monitoring and control of the power system. Generation, traditionally it was more of a concentrated in thermal, hydro kind of generation, but now in addition to your conventional energy sources, a lot of renewable energy sources are coming, in which pump hydro, geothermal, biomass, hydro, solar, wind are more common. And because of that, you are kind of distributing the generation domain across the value chain, whether it is transmission or distribution or even the consumer premise. Transmission domain is still our traditional transmission network, where long distance you see the power transmission from concentrated load from generation side to concentrated load side. Distribution system will see a lot of changes because in future you will see a lot of integration of renewable energy sources or any other such kind of distributed generation with energy storage. So you will have a lot of new energy resources coming up in the distribution system at distributed level. Because of all those things, you will see a lot of regulatory challenges, and we are right now witnessing those problems. And what are those main challenges? First challenge is that although we are having a lot of new renewable energy sources or the new technologies in the system, it is very hard to convince the utility companies that what are the benefits of these kind of solutions. Then energy efficiency is the benchmark for smart grid, but it is not necessary that once you get the energy efficiency, you will get economic efficiency as well. So most of the time, utilities are concentrated towards economic efficiency than the energy efficiency. So telling them the benefit of energy efficiency is another challenge. Now, because of the huge intervention of different IT and communication technologies, we are seeing that the smart grid implementation is happening in phases. So it is very difficult to tell people about the advantages of overall smart grid technologies. Policies we need to create so that we can use the best of the technologies which are available as part of a smart grid. We need to develop some mechanism for different stakeholders so that they can get some incentive in the deployment of smart grid technologies or in the promotion of different demand response schemes. We need to encourage the system operator and utilities to play a more active role in addressing the future economic and technical and social challenges. Long-term clear-cut policy is required because smart grid implementation requires a lot of policy intervention. Electric vehicle demand response and in fact renewable energy sources integration require sophisticated policies which are still not there in the system. We are not in a position to handle huge amount of data. In fact, energy theft is not that big concern, while data theft is becoming more concern for the utility companies. Other devices like smart meter, phasor measurement unit, or other smart home solutions are generating a lot of data. We are not having sophisticated tool to handle those kind of data sets. So that's why data protection is another issue. And then standardization in smart grid is another challenge because different kind of devices having their own data standard or the protocol standard. Seamless integration of data is a biggest challenge in the smart grid domain. What are the different agencies we see in smart grid area? We have IEEE, as you may be knowing, then International Electrotechnical Commission, National Institute of Standards and Technology, SIGRE, UCA-IUG, that is Universal Communication Architecture International User Group, EPRI, NREL, ESA, NERC. These are the main agencies worldwide which are responsible for the deployment of different smart grid technologies. In India, we have India Smart Grid Forum, then India Smart Grid Task Force, which was initially created by Government of India, but it was diluted, and then National Smart Grid Mission was created in January 2016. So it is a body which takes care of the different smart grid pilot project implementation in India. Then to some extent, CPRA is also funding some of the smart grid pilot projects. And then you see different utilities are also working on different smart grid aspects. Now, particularly if we talk about the renewable integration, we see that in future the role of conventional energy sources will reduce drastically, because as per current target, the renewable energy penetration will be almost 90% by 2050. So you can understand that how the role of renewables is coming up in the market. But it is also adding more challenges in the power system network. What are the challenges? So first biggest challenge is the intermittency, because say solar is available during daytime, and then it is available only when we have the clear sky. So the solar output depends upon season, weather, and other parameters which require accurate forecast. So in addition to your load or generation forecast, you need accurate weather forecast as well, so that you can get the real picture about the renewable generation in the distribution system. So that intermittency is creating a lot of challenges. Sudden cloud cover will ramp down your generation from peak to zero. In fact, the problems are already coming in the distribution system, especially like in Gujarat, when we see where we have huge solar power generation. In the evening, suddenly when we see the sunset, the demand of around 5,000 megawatt comes up suddenly. So 5,000 megawatt is not a small demand in the system, and addressing that demand require lot of technology intervention. Then voltage and frequency control, because most of these sources do not have reactive power generation. So although new converters which are coming up in the market are having now the converter control with reactive power generation, but we have lot of such installation in the solar, in the distribution and transmission system, where the solar generation happens with the help of the first generation or the second generation of inverters, where we do not have reactive power management capability. So this again poses the challenge how you will control the voltage and frequency of the system. Then sudden generation loss leads to transient angle and voltage instability, and that's why we need real-time monitoring and control of these kind of energy sources. If we have the transient coming in the system, we have only few seconds of time window to control the operation of the power system network, and that kind of control is not possible with our conventional SCADA or ADMS system. We need more sophisticated tools for addressing the transient phenomena or voltage instability phenomena. Stability issue is more challenging because inertia-less generation will reduce the overall inertia of the system. As I mentioned, that in conventional power system, since thermal energy, thermal power plants have huge mass in terms of big generators, so their inertia has the capability to absorb a small size of faults, and the system doesn't get out of synchronism. But once we have more solar penetration, which is not having any inertia, will have more challenge in terms of transients, in terms of faults, and how we will address the stability issue in the system. Then power quality issue will also come because of harmonics, flickers, and under voltage right through in the system. Then optimal power management, you need new tools for in terms of ADMS or microgrid energy management system, which can give you better visualization of the such kind of renewable energy sources. Then adaptive operation scheme, because we have now bidirectional power flow. That means the conventional protection schemes are no longer working. You need adaptive protection scheme where you can address the bidirectional power flow, because right now the system is designed for unidirectional power flow. Once the power flow reversal happens, system will consider it as a fault and relay will operate. But when we have more renewable energy penetration, the bidirectional power flow will be the common phenomena, and we need to change our protection settings. So these are the challenges we saw in the renewables as of now. Let me discuss about one case study, or in fact, this is Indo-US project which we have executed in our campus. There in India side, we have 15 organizations, and from US side, we have 15 organizations working on the development of next generation of a smart distribution system with the renewables and storage. There in US, we have 5 demonstration pilots, and in India also we have 5 demonstration pilots. In India, we have 3 pilots which are being executed by IIT Kanpur. One is urban pilot, then semi-urban, and then rural pilot. One semi-urban is being executed by Netra NTPC, and then urban pilot, another one is being executed by Terry. So today I'll talk about the 3 pilots which are being executed by IIT Kanpur. So that is rural, semi-urban, and urban pilots. So rural pilot is being commissioned in a village called Harnu, which is around 45 kilometers from campus. And Dakshinanchal Vidyut Vitran Nigam, that is DVBNL, is the utility in Harnu village. So if you see the structure of the pilot, we have 2 hamlets. One is Chabba Nevada, another is Bargadia Purva. These 2 hamlets are being fed from utility grid separately. So they have 49 kilowatt kVA of utility grid connection. And then utility grid is connected to our local control center. Here in this local control center, we have hybrid inverter where you have 100 kilowatt hour energy storage system. This is the lithium ion energy storage system which is connected to hybrid inverter for providing the power supply. Then we have in Bargadia Purva, we have 30 kilowatt of solar which is connected to local distribution system using grid tie inverter. We also have 30 kilowatt of hybrid biomass. So this particular substation which we have created in the Bargadia Purva has different energy sources, and load is for the village as well as for the street lights. In this particular setup, we have microgrid controller which decides which source should be dispatched at what time depending upon the economics and the availability. So most of the time in daytime, you will have first power to be dispatched from solar PV panels, and if there is an extra power, this is exported back to the grid. In the evening time, first priority is given to biomass system. So evening 6 p.m. to 10 p.m. Hybrid biomass system works. Once it exhausts, then we switch over to battery energy storage system. So this priority has been decided. Then another important feature is the power flow between these two village hamlets. So we have another 25 kilowatt AC/DC AC converter where you can share power from one village to other village. Say for example, if one side utility grid is not available and load is more than the generation, so first it will import power from another hamlets, provided it has sufficient generation. So in that way you can exchange the power internally even if the grid on either side is not available. In case of Chabba Nevada, we have 100 kilowatt hour of lithium ion battery energy storage system and 70 kilowatt of solar. So in this particular rural microgrid, the major challenges are how you will interconnect two different microgrids. In fact, this is one microgrid, this is another microgrid, and we are connecting them to each other via customized AC/DC AC converter, which was designed by us, and then later it was manufactured by a company called Statcon. So the important component is AC/DC AC converter, then microgrid controller, and then operating philosophy based on what energy resource will be dispatched first. So in that way you will see that in rural setting also the microgrid and other renewable integration activities can be performed with the help of support from local utility as well as from the local village people. So these are the some real pictures of the village. This is our biomass plant where you will see that it is a digester. Then in the digester, once the methane gas is generated, this is a balloon which stores the methane gas. The output of this digester is the bio fertilizer. So liquid and solid fertilizer is used for local irrigation activities. This is our control room and solar PV system in Bargadia Purva hamlet, and this is independent solar pump given to them for irrigation purpose. Now this is a control room at Chabba Nevada. There we have ground mounted solar PV system, and these are some glimpses of our meetings which happens in the village. Then second pilot is our smart grid semi-urban field pilot. So as per definition, semi-urban is that area where we have mostly single-story houses scattered in a large geography. Since we have the faculty houses replicating to this semi-urban setup where we have individual houses scattered around. So we took campus lane 32 and 33 for implementing the semi-urban pilot. So in this pilot, we are having 5 kilowatt peak rooftop solar in 30 houses. We have 2 battery storage systems, and at the end of both lanes, in one lane we have 140 kilowatt hour lithium ion, and another we have 100 kilowatt hour lithium ion battery storage system. So we have distributed solar PV and concentrated battery storage. The advantage of having this kind of setup is that, as you know, that when we have grid connected solar PV system, once grid is not available, your output from the grid connected solar PV is also 0. So to address that challenge, we create the local distribution ring with the help of our battery storage system. So we will disconnect lane 32 and 33 from rest of the campus grid. We create local island having these two battery energy storage systems. So this hybrid inverter, if you see in this figure, this will be acting as a grid forming inverter, and this will give voltage reference to those rooftop solar PV systems, and your solar power output will keep on coming to the local islanded grid. So the advantage of so the limitation of not having solar power output under outage condition is addressed with the help of this kind of islanded operation of the system. So this we realized over there. Then we have two EV charging stations also to check the vehicle to grid and grid to vehicle capability. Though we have right now vehicle in the campus which can only charge but cannot discharge, but in future we are planning to modify the vehicle and the development of bidirectional power converter so that the power from vehicle can also be pumped back to the grid. Then these all are being monitored through our local SCADA system that I'll show in next few slides. This is our architecture or single line diagram of our semi-urban pilots, where we have different houses with solar PV. Then the substation, which is feeding both of the lanes, is connected to our SCADA system for monitoring of the important parameters of our semi-urban pilot. In urban pilots, basically this urban definition is the area where we have multi-story buildings. So multi-story apartment of faculty members we have considered for implementation of urban field pilot, where the main objective is to minimize the consumption of the diesel generator, because we need diesel generator whenever there is a power outage. Diesel generator used to run for common lighting and the lifts. So we replace the diesel generator by solar PV setup as well as the battery energy storage system of 50 kilowatt hour. So in that case, for any power outage, we are not depending upon the diesel generator, while this particular setup will support the lifts in the apartment and the common lighting which are required for that particular building. So these are the three pilots which we have in the campus. In urban, we also have the thermal energy storage system. So if you see, this is our thermal energy storage system, which has a capability of 775 ton hour. So this particular tank contains the phase change material. So this phase change material is cooled down to -8 degrees centigrade, and cooling is retained with this thermal insulated tank. So whenever the air conditioning load is required, we, rather than adding that load to the grid, we connect to this particular thermal energy storage system, and the air conditioning requirement is fulfilled by this thermal energy storage system. So this has a main advantage that during peak load condition, generally this happens in peak summer during 11 a.m. to 2 p.m. So during that period, when we have peak load condition, we can cut off the air conditioning system from the grid and continue to pump air conditioning cool air from the thermal energy storage system. This is our smart grid control center where we monitor all our pilots, and in fact we have our own advanced metering infrastructure applications developed and deployed here, where we can monitor the smart meter data at very fast rate. So we have configured to share the data after every 1 minute, but you can go up to 30 seconds as well. Then we are building our own advanced distribution management system. This is very important because in future when we go for smart distribution system, we need advanced distribution management system for better monitoring and control. The conventional distribution management systems are developed with more legacy IT technologies, and that's why those have lot of limitations. This ADMS system we are building with more flexibility, and we are using common information model for real-time data exchange between different software applications. So our complete database is built around common information model for better interoperability. And then in fact, topology processor, state estimator, distribution system power flow has been already implemented. We are right now implementing fault location, volt power optimization in this ADMS. Switch order management, loss minimization are some functions which we will complete by end of June. Geographical information system, for that we have used OpenStreetMap, and that is being integrated with our ADMS system. So in total, if you see our ADMS architecture, it is a next generation ADMS system which has more flexibility and better integration of data and software applications. So with this, thank you very much for listening to me. I'm open to questions so that I can answer your queries.
So now session is open for discussion. Please, if you have any query, you may ask. Anyone? Can you hear me, Rajesh?
No one has any question?
Sir,
Someone? Yeah. Yeah.
I'm having one question that, sir, you in the beginning of the slide you have told from RTU to SLDC, then RLDC, then to NLDC, there are some communication gaps or the time loss of some time is done in terms of 10 seconds or 15 seconds. Sir, can you please elaborate what kind of time loss? Because it is the time loss consists of one communication, or is the measurement and all in the sending of data to from one server to another? Because nowadays we are having high bandwidth of communication like optical fiber and 4G and 5G. Then why such communication loss is there?
See, SLDC and RLDC are situated in different cities, right? You are relying only on the public service provider. Generally, you use either MPLS or maybe to some extent 3G and 4G communication for data sharing, right? Now, from RTU to SLDC, you have inherent delay because RTU is based on pooling of the data, right? So pooling means you have one server, and if you have 100 RTUs, the server goes to each and every RTU and asks for the data. So that is the pooling mechanism which was developed traditionally, because at that time we were having the limitation on the bandwidth of the system. So still we are following that kind of architecture, which is not basically good for current IT infrastructure. We need to go for more sophisticated subscriber publisher module. But since the SCADA system is a legacy system, it still polls the data. Once you start polling the data, you have inherent delay of 5 to 10 seconds, right? Now, once you reach to server level, SCADA has its own processing limitation. It will take its own time to process the data. Even if you have very fast data communication, the software has itself some delay, maybe 2 to 3 seconds of delay, or to some extent 4-5 seconds of delay for processing the data and further sending data to another control center. So basically, when you send data from SLDC to RLDC, you use a protocol called ICCP, that is Inter Control Center Communication Protocol. So what will happen? From RTU, you have got data in 60870-5-104. So 104 protocol is the default protocol you use for RTU to SCADA server data communication. Once you receive data at server, you kind of decrypt the data, because you want to remove the protocol component and receive the data from that data packet. So it has its own delay. Then you process for possible outlier or missing data, or you replace with any calculated data. So then you have some more delay in that. Now from SCADA, you have to again pack that data into ICCP protocol, right? So then again you have some processing delay. From ICCP sending end to receiving end, you have another communication delay, right? So delays are involved in each and every step, and because of that, you are having that kind of total delay, as I mentioned in the slide, right? So this is not because of your fast communication capability which you have right now. It has because of the inherent processing limitations we have in the different softwares.
Okay, sir. Okay, sir. Thank you, sir.
Anyone else?
Good evening, sir. Myself, Srikar. I'm studying MTech in NIT Agartala. Sir, regarding IT and OT applications, you have said OT, like operation technology side, we should have some minimum idea regarding IT side. Like, what exactly knowledge should we have, sir, regarding IT side?
So for from IT side, you should have the knowledge about how the data communication happens. So in fact, computer network knowledge is the most important thing. Then you should have the knowledge about various software protocols we use in IT side or OT side, both sides. Say when we talk about TCP/IP or when we talk about Ethernet, most of the people are not aware whether Ethernet is hardware or software, right? Or whether Ethernet is protocol or a technology. So those kind of small things are creating limitations in our understanding. So in fact, understanding about the TCP/IP, understanding about the OSI 7-layer architecture, computer network, and the protocols which we use in the power system network are very much essential. Then when you talk about information technology, you should have the basic idea about object oriented programming, how you do the programming, what is web service, how you create API call. All those things are very much essential, which we try to neglect because we do not have that kind of exposure in our regular curriculum.
Thank you, sir.
Anyone? Okay, so I think right, but I have a one query in this the case study related to rural area. You have connected two hamlets, na?
Yes.
Right. So right now, have you proposed any billing structure for that because you are connecting two microgrids? So who's that connecting line is? Matlab, who belongs to that connecting line actually?
So basically, if you are sending power from village A to B, then A will bill to B, and when B will send to A, then B will bill to A. So right
Then
now
who?
we have not done the commercial calculation like who will bill, but we are assuming that both will need power. So sometime in future it will automatically cancel out because at say on day one someone is village A is sending power to B for say 1 hour. Second day B will send to A for again 1 hour. So it will kind of cancel out.
Okay, so there is a matlab, net will be zero.
Net bill will be zero, right?
Okay, thank you. Anyone else? Right. Dr. Vikram, so
Yeah, good evening, sir.
Good evening.
Sir, I have a small query. Actually, in your Hamlet, you have said that you are using AMI for smart metering. So, is there any reason we are not using AMR instead of AMI other than two-way communication system?
AMR doesn't have a capability to remote disconnect the meter because it is only for meter reading, AMR. So you can only use meter reading, not the two-way communication. So it's a one-way communication. You will only read the meter data. But sometimes you want to disconnect the meter remotely when someone is not paying energy bill. That is only possible when you deploy the AMI infrastructure.
Yeah. So that is only for two-way communication system.
Yes.
Yeah. Thank you, sir. So actually, myself co-coordinator for this ATAL DP. So I have seen the presentation thoroughly, starting from the beginning of smart distribution grid. So you have nicely presented the seminar or the deliberations. You have highlighted so many things, starting from power system automation, recent changes in power sector, even the evolution of different IT and OT systems, how they are interrelated, how they are not dependent on each other or interdependent. So all these things are, I hope, has greatly helped the audience or the participants. And I hope if there is any doubts that remains with the participants, they may link up with you through emails.
Sure. Sure.
So with this, it comes to the end of today's sessions. I thank you from the deep of my heart for being a part of this PP. And I thank you on behalf of NIT Agartala and Electrical Engineering Department particularly, as well as from the participants and the coordinator and head of the department. I thank you once again, sir, for
Thank
your
you.
deliberations. Thank you.
So Dr. Vikram is the one of the coordinators of this program also.
Okay.
He is lead faculty there. Now I request everyone please turn on your video so that we can capture one quick also. Everyone please. Rajesh, you just increase the frame so that everybody can be captured.
Yes, sir. Yes, sir.
You can
Sir, I'm
increase.
taking one
You can.
screenshot. Everybody, please turn on the video. I am taking one screenshot for attendance purpose. Deeptalu, Debashish, Norin.
That's okay, no issue. Yes.
I'm taking.
Okay. Right.
Okay, sir. Taken.
Thank you. Thank you, Dr. Ankush.
Thank you. Thank you very
For-
much. Okay.
Okay.
Bye. Bye.
Sir,
Bye.
can
Bye.
you
Good night.
please share that PPT with us?
Yeah, sure. I'll share.
Okay. Thank you. Thank you very much. Bye.
Thank you, sir.
Thank you, sir.
Welcome. Welcome.
Thank you,
So
sir.
now, thank you. Now, so again, we will connect tomorrow at 6:50. This is my humble request to all of you. Please ensure 100% attendance during the online, because you can connect from your home. Because there is a requirement of attendance also as per the AICT. So now this is a technology, easily we can connect. So now we will meet tomorrow. Thank you. Thank you very much. Now I'm disconnecting.
Thank you, sir.
Thank you, sir.
Thank you,
Thank you,
sir.
sir. Thank you, sir.